This module will discuss some of the basic features of the Madden-Julian oscillation, or MJO. The MJO is the dominant variability in precipitation and many other atmospheric and upper ocean variables on timescales of 20 to 100 days, also known as subseasonal or intraseasonal variability. Although it has noticeable impact on weather around the globe, it is still not well represented in most numerical models of the atmosphere and ocean, and the underlying dynamics that control the MJO are still not entirely explained. What became known as the MJO was first noticed in the 1960s, but was popularized by a set of papers by Madden-Julian in the early 1970s. They documented distinct minima and maxima in surface pressure at various ground stations in the tropics every 40 to 50 days, such as in the top plot, which illustrates a raw time series of pressure at the top and a 45-day bandpass filtered time series of pressure at the bottom. This is from the West Pacific at Canton Island. Rowinsons as the payload on weather balloons captured similar variability in zonal wind at various altitudes, shown here at the 150 and 850 millibar pressure levels. By running a bandpass filter on time series of various variables, they were able to demonstrate a statistically significant variability in the tropical atmosphere at the subseasonal time range. An example of bandpass filtered zonal wind and surface pressure over a 4-year period at the same location in the West Pacific is shown here. High amplitude variability, like that in this blue circle, corresponds with a strong MJO, while other periods of time show little variability at this particular subseasonal band. These would be considered weaker MJO signals, or perhaps it's not even an active MJO. Since these early papers, the MJO has been extensively studied and linked to variability in weather events all over the world. However, as we said before, a complete explanation for what drives the MJO is still unknown. Time series of precipitation with similar variability also occurs with the other variables that we discussed and some other variables that we haven't, indicating that the MJO is likely convectively coupled. Shown here is a time series of radar-derived precipitation from the central Indian Ocean, created from data collected during the Dynamo Field campaign in 2011, a multinational, multi-agency field experiment aimed at better understanding the initiation processes for convection in the MJO. Over the 3.5-month-long period plotted here on the x-axis, 3 broad peaks, here's one, here's another, and here's a third, of precipitation are denoted, and these represent the 3 active peaks of convection in the MJO, each separated by a minimum in convective activity. In this example, the broad peaks are separated by about 30 days. Superimposed onto the MJO signal are several higher frequency rainfall events, denoted by the narrower spikes in the rainfall time series, both in this event, and also into the December event. These spikes were associated with other equatorial waves, especially Kelvin, westward propagating inertia gravity, and equatorial Rossby waves. Thus, a variety of different wave modes exist simultaneously at various frequencies, and they can constructively or destructively interfere with one another. For example, if the downward branch of an inertia gravity wave is present at the same time as the upper branch of an MJO, like right here, then relatively little precipitation may occur at the location where the inertia gravity wave is suppressing the convection, even though the larger scale MJO feature supports convection. However, because the frequency of inertia gravity waves is much higher than that of the MJO, as we might recall from the wave number power spectra of tropical outgoing long-wave radiation, the rainfall recovers rather quickly after a minimum, and spikes back up the following day in that particular example. The MJO manifests itself primarily as variability in convection over the tropical Indo-Pacific warm pool, roughly within the orange ellipse shown here. Convection in the MJO is often first observed in the left part of the ellipse over the Indian Ocean. A primary characteristic is its low frequency, with maximum rainfall occurring only approximately once per month or less, as we saw in the last figure. Another defining feature of the large-scale convective region during an active MJO is that it moves eastward at speeds of, on average, only about 5 meters per second. This is much slower than the propagation speeds of free Matsuno equatorial modes. The MJO impacts weather around the globe, and a few examples are highlighted here. For example, subseasonal variability in surface temperatures in the Arctic have been linked to MJO activity in the tropics. Rainfall and severe weather events, such as atmospheric rivers on the west coast, Santa Ana wind events, or severe weather outbreaks in the central U.S., rainfall in the southeastern U.S., have all been linked to the MJO. The MJO modulates monsoon activity in the purple areas and tropical cyclone activity, roughly in the red areas, in regions where TCs occur. And many other examples have been documented in scientific literature and are not shown here, but I could probably color in just about every region on Earth with some impact that the MJO has on regional weather at subseasonal timescales. The basic circulation pattern of an MJO when convectively active is closely described by the Gill-type response to equatorial heating. The response to symmetric latent heat release in this region, centered on the equator, is a combined Kelvin and Rossby wave structure. Convergence is seen on the equator centered near the convection, which is the Kelvin wave part of the response, while two off-equatorial gyres develop slightly west of the longitude of the convective maximum. That's the Rossby wave component of the response. This pattern tends to become coupled to convection as it moves toward the east. However, the circulation becomes more complicated for cases when the maximum latent heating is not symmetric about the equator, which is especially common during boreal summer when the MJO and the South Asian summer monsoon interact to form what some call the boreal summer interseasonal oscillation, or BSISO. The cloud pattern associated with MJO variability sometimes resembles the circulation response to Gill-type heating. In this figure, the equator is located along the horizontal white line right here between the islands labeled Malay and Gan. One can somewhat envision how the cloud population is focused along the equator ahead of the area of maximum latent heating shaded in red. The clouds to the north and south of the heating maximum are contained within these gyres and even show some sign of positive relative vorticity. To the immediate west of the latent heating maximum is an area with little convection, which is underneath this orange arrow. This is reinforced by the equatorial flow of drier air from these slightly higher latitudes into the equatorial region around the Rossby gyres. Other waves are superimposed onto this coupled Kelvin-Rossby wave response to heating. For example, a relative void in convection is seen immediately east of the red ellipse, but even further to the east is another region of active convection. This may represent something like an inertia gravity wave superimposed onto the larger scale, more slowly varying MJO circulation, or perhaps this is an upward branch of some other smaller scale wave feature. Because of its impacts on weather globally, great interest is taken in objectively identifying and tracking the upward branch of the MJO. A common way of doing so uses principal component analysis and projects horizontal fields of outgoing long-wave radiation observed and horizontal wind observed at various pressure levels onto the first two empirical orthogonal functions, or EOFs, that describe about 25% of the variance associated with either field. EOFs 1 and 2 respectively correspond to principal components, or PCs, 1 and 2. The methods create an MJO index that can be used to describe the magnitude of the MJO signal and the location of its upward branch in the tropics, particularly the longitude. The first two EOFs can be illustrated as special patterns that look like what is shown on this slide, with the first two EOFs for two commonly used MJO indices, the real-time multivariate MJO index, or RMM, shown at top, and the OLR MJO index, or OMI, shown down here at the bottom. The blue shading indicates where convection is located in these EOFs. You can see that they look quite similar, although the order of the PCs is just reversed for the OMI relative to the RMM. The two EOFs are very similar in structure. One EOF has convection centered over the maritime continent, with regions of suppressed convection located to the east. The other significant EOF contains convection that is centered near the equator, but more located over the West Pacific, with suppressed convection in the Indian Ocean. While the OMI uses only OLR, the RMM index uses both zonal wind and OLR. How the real OLR or zonal wind field projects onto these two EOFs determines the value of each index. And of course, the EOFs for zonal wind will look a little bit different than that for the OLR. Mainly they'll be in quadrature. Such methods of identifying the MJO separate the MJO into 8 phases, which simply describe all potential combinations of the signs and relative magnitudes of the first 2 principal components. The 8 phases make a cycle that is often seen to repeat itself. As an example, a positive PC1 and positive PC2 would indicate that the convection is located over the maritime continent, where the blue colors were seen in the previous figure. Basically here and here. As seen in the top left, having positive values for both PCs means that we are in phase 5 and 6 of the cycle. We'll show what that looks like in horizontal space soon. Negative magnitudes for both PCs would tell us that convection is particularly suppressed in those blue regions, and the RMM index would be in phases 1 or 2, with the MJO upward branch, and perhaps convection, located more over Africa or the Indian Ocean. The figure on the right is called a phase space diagram. It is a common way of assessing the magnitude and location of the upward branch of an MJO. On the x-axis is the value of PC1, and on the y-axis is the magnitude of and value, also the sign, of PC2. The axis labels denote the phases that correspond with each pi slice of the phase space, and the approximate location within the tropics of each of these phases is denoted by the parentheses in the labels. The circle at the center of the plot denotes a magnitude of 1. Generally, the index must have a magnitude of at least 1 for a strong MJO to be considered active. Note that the magnitude of the index is simply the square root of the sum of the squares of the leading 2 PCs. These types of plots illustrate a time series of RMM, or whatever other index, depending on what's plotted. For example, the red dot might be collected at some point in time by projecting the real OLR and zonal wind horizontal structure onto the leading 2 EOF structures, for in this case OLR and zonal wind in the RMM index. At the red dot, I have a large negative magnitude for PC2, meaning that the convective pattern is opposite that seen on the right-hand side here, and a positive PC1, meaning that the spatial pattern of convection projects well onto the spatial pattern seen here on the left-hand side of this. Based on this, we can conclude that the upward branch of the MJO is located over the Indian Ocean, and we would say the MJO in this case was in phase 3. The different colored lines in this example show daily values of the index plotted over the course of 3 months, with each month denoted by a different color: blue October, green November, and this magenta December. Because the MJO propagates toward the east, the line generally moves counterclockwise in the phase space displayed. You can see how the magnitude of the MJO varies with time as well. The further from the center of the circle a point is, the stronger the MJO signal. The typical anomalous OLR structure seen when the RMM is in each phase is shown here, with the green and blue shading indicating regions of anomalously positive precipitation. At the top, in this particular example's phase 2 structure, which features anomalous rainfall over the central and western Indian Ocean, really over the entire Indian Ocean with a peak in the central Indian Ocean. As the phase progresses, or the MJO moves eastward, the rainfall also moves toward the east. That's really just a manifestation of the circulation in the upward branch of the disturbance. And by phase 7, the convection becomes partially decoupled from the circulation, as the circulation moves over regions where convection is not well supported by the environment on the equator, such as in the downward branch of the Walker circulation in the East Pacific. The atmosphere is stable and SSTs are low. Well, you do see a little bit of a signal down here in the South Pacific convergence zone as the wave passes by. Any convective signal that persists beyond this point generally moves rapidly through the Western Hemisphere in phases 7 through 1, before potentially repeating when the upper branch of the wave reaches the Indo-Pacific warm pool again. Note again that these are anomalous rainfall signals associated with the MJO. Other variability is always superimposed on top of the MJO signal. Indices such as RMM and OMI try to find the component of the total signal that looks like these spatial patterns. The same example of a phase space diagram shown before is seen at left in this slide. If we start following the line where the word start is seen in the top right quadrant and follow the line counterclockwise, we see one active period over the Indian Ocean along the blue line here in October, and then we can continue wrapping around into the green line and we see another over the Indian Ocean in November. And if we continue to follow the line around, an apparent stalling of the MJO as it approaches this unit circle where there's not really a strong MJO, but nonetheless some signal located over the maritime continent that doesn't really seem to move much. On the right is a Hofmahler time series, satellite-derived rainfall with locations in the tropics denoted along the top axis. So this region right here, where this vertical black line is centered in the Indian Ocean. 3 broad regions of enhanced precipitation are seen to propagate off toward the east. Each is associated with an upward MJO branch passing through. In fact, a circulation signal associated with the MJO moved all the way around the world between the November and December events depicted here. However, the RMM index essentially got stuck over the maritime continent because convection persisted there, and that convection projected onto one of the first 2 principal components. This is an example of one limitation of objective algorithms that are based on PCA and projecting fields onto these first 2 EOFs. They don't necessarily portray the MJO signal correctly when the convection is weak. This can happen sometimes when a circulation signal is present over the East Pacific, over here somewhere, but there's no convection signal present because equatorial SSTs there are too low to support convection. And I should mention that this Hofmahler is average between a latitudinal band like 5 north to 5 south or so. It's very close to the equator. And we'll further discuss these events in the paper discussion this week. Some other indices are used for MJO identification, and a list is shown here. If interested, you can take a look online for details about some of these other indices, which use OLR or velocity potential in various ways, but still project fields onto the leading 2 PCs of subseasonal variability regardless of what variables they use. One of these indices is the Velocity Potential MJO Index, or VPM. It replaces OLR with velocity potential, but also uses the zonal winds like the RMM index. The velocity potential is primarily concerned with the irrotational component of the large-scale flow. So inherently, it's fundamentally trying to track any potentially existing gravity wave component of equatorial disturbances that propagate eastward. The velocity potential is essentially a smooth divergence field, such that negative velocity potential represents divergence. It's really more large-scale divergence. Velocity potential is defined such that its gradient describes a divergent component of the wind. The Laplacian of the velocity potential is 0 for incompressible flow. Based on their mathematical definition, velocity potentials smooth out areas of divergent flow. It is often tracked at 200 hectopascals as a diagnostic of where the upward branch of equatorial waves are typically present. In this Hofmahler diagram, brown areas, or even yellow embedded, represent anomalous large-scale convergence at 200 hectopascals near the tropopause, which would correspond via mass continuity to anomalous downward motion beneath this level. Green areas denote large-scale divergence aloft, or at least these are velocity potential anomalies, so it's a large-scale divergence anomaly aloft, which is consistent with anomalous upward motion beneath. These velocity potential anomalies are easily seen to move eastward throughout the tropics. At times, their circumnavigation is also apparent. Anomalies of velocity potential can also be tracked on plan view maps, with forecasts into the future projecting where negative velocity potential anomalies may exist. This can provide some crude, medium-range predictability of generally what part of the tropics convection may be more active, and many times, negative velocity potential anomalies in the upper troposphere correspond with regions of active MJO convection, at least close to the equator. In this example, a region of anomalous divergence aloft is seen to be present over the Indian Ocean and forecasted to move eastward toward the maritime continent over the following 2 weeks. Forecasters interested in tropical cyclone activity also pay attention to the propagation of velocity potential anomalies because they may provide some insight, for example, about the potential for increased tropical cyclone activity as a region of anomalous tropospheric upward motion approaches from the west.